You may have heard the term dark matter without a convincing explanation of what it actually is. That's because no one really knows. Many astronomical observations have shown effects that cannot be explained by the matter that we see around us. For example, galaxies seem to be rotating too fast, which suggests that they contain a large amount of extra matter that does not emit or absorb light. The effect of this new type of dark matter can also be seen in larger systems, and in fact, galaxies probably couldn't have formed without it. Our observations show that there is 5 times more dark matter in the universe than the ordinary visible matter that we are made of. Many of us here at the Institute for Particle Physics Phenomenology in Durham are working to try and understand exactly what it is, and to see it directly interact with normal matter.
One thing that we do know about dark matter is that any interaction it has with ordinary matter must be very rare. So we have to build incredibly sensitive experiments. One example of such an experiment is Super CDMS, of which we have a model, where the white plastic discs represent and are the same size as the metallic crystals that will be used. Super CDMS will begin collecting data in Canada in the early 2020s, and it is sensitive enough to detect one nucleus recoiling after a dark matter particle has hit it, due to the vibrations this causes in the germanium crystal lattice. In order to be this sensitive, Super CDMS must be kept at chilly -273 degrees Celsius. We can use computer simulations to model potential types of dark matter and design the experiment to increase our chances of a discovery. An added difficulty is that the vibrations can also be caused by normal matter, and since we aren't interested in these results, we call them background events. Again, we can use computer simulations to study the expected background events for different experimental designs. These background events are caused by the natural radiation that surrounds us. It comes from the atmosphere above us, the rocks below us, and bananas. If we try to run the experiment in this room, we would only see background events, here represented by red lights. In order to see the dark matter, the blue flashes, we need to stop this radiation reaching our detector. We can start by going underground so that the ground above absorbs radiation. Going further underground will reduce the atmospheric radiation even more, but there is a practical limit. The deeper we go, the more difficult and expensive it becomes. Super CDMS will be placed in a particle physics laboratory called SNOWLab, 2 kilometers underground. We also need to stop radiation from the rocks in the Earth's crust, so we place shielding around the entire experiment. Super CDMS will have layers of lead, polyethylene, and water with a total width of 2 meters. As with going further underground, adding more shielding would be better, but expensive. The high cost of the shielding is partially due to needing to use very pure materials, which contain as few radioactive atoms as possible. The current technological level allows us to have a purity of about 1 part in 1,000, meaning the materials are 1,000 times less radioactive than they were originally. With each additional step to our design, we have seen fewer red flashes. This is great news, as it shows how much we've reduced the background radiation. Now we just need to spend 5 years watching our experiment and count the blue flashes. Here we're lucky, and we can time warp through the 5 years and analyze our results. We still have background events in our detector, as we can't block out every single bit of radiation. We can again use computer simulations to tell us that an incoming particle interacting with an electron rather than a nucleus, interacting on the surface of the detector or interacting in more than one detector, is far more likely to be normal matter than dark matter, so we can ignore such events.
After the experiment has run, the data will be analysed. And if dark matter has been detected, we can determine its mass and the probability that it will interact. This measurement would only be the start though. The real task will then be to determine what this particle actually is and how it relates to the rest of the known matter. And once again, computer simulations will be our guide. The search for dark matter, like most research, is a bit like the search for a needle in a haystack, without the guarantee that there is one to find. But research is about developing methods to search systematically, and these methods and the insights that we gain along the way, be it technological advancements in cryogenics, electronics, and computer science, or unexpected discoveries, help make it worth it. One day, these discoveries may have applications that haven't even occurred to us yet.